Thanks to the organisers, to Jan and Barbara for putting together this meeting. This session will be on laboratory insights into large earthquakes, great earthquakes. So my name is Dan Faulkner from the University of Liverpool, and I'll be leading this session, so hopefully everyone's going to keep nicely to time. Our first speaker, hopefully, is Giulio de Toro, who has really led the way in the past few years, I think, in terms of understanding high-velocity friction. So he's made some really great contributions, and as a field geologist as well as an experimentalist, I think he can give us some real insights into what he'll talk to us about today, which is the geology, physics and chemistry of earthquakes in carbonate-hosted rocks.
Okay. Thank you, Dan. Two very nice words. So I will ruin whatever is said before. Actually, I will mainly talk about perhaps some about processes occurring during seismic sleep. The title was too ambitious. And it's related to, some rocks are pretty common in continental belts, but also in ocean sea floors. And this kind of work is funded by the European Research Council, and especially it covered the salary of many people that worked with me in the last 10 years. So I'm really grateful to the ERC. So I will talk about very shortly why we're interested in earthquakes in carbonate-built rocks. And then I will talk about some main experimental results. And based on this, I will move more in detail about the processes occurring at seismic sleep initiation and perhaps during and at the end of seismic sleep, so also fault healing. And why we're interested? Well, as an Italian, we have a lot of earthquakes occurring in my own country, but also in Greece, and well, it's not shown here. Excuse me, perhaps it's, yeah. And this is, as you can notice from this map, the blue color are carbonate-built rocks, and by carbonate-built, I mean calcite and dolomite are the main minerals of these rocks. So these are limestones and dolstones. And you can see the epicenters, they nicely overlap, especially in central Italy or in Greece, with these thick sequences of carbonates. And this according to this catalog from INGV and Greece. And if you go and look at in the field one of these faults, these are faults in central Italy. They put in contact, for instance, these are Holocene and Quaternary deposits, and the fault passes here, and there is a thick damage zone. And the damage zone is cut by, excuse me, okay. I'm a bit, and if you look in detail at the slip surfaces, it's cut by mirror-like surface like this one. Now there is a coin for scale. And if you zoom, and look with a scanning electron microscope from the mirror towards the rock, you will find this kind of fabric. Now the scale bar is only 5 microns, and this is calcite, perhaps crystallized during seismic sleep. This is something I will discuss today. And well, if you think about great earthquakes, well, and if you go at the, where people were talking today, a bit more to the north, so where the Naxa plate goes beneath the Caribbean plate, it looks like there are some pretty thick sequences of carbonate biogenic oozes that are made by the skeletons of these microorganisms, benthonic and so on. This is coccolite in this case. You see they're about 10 microns or 15 microns in diameter. And it seems that some ruptures actually during big earthquakes can propagate through these materials. So carbonates are perhaps also pretty important also in subduction settings, so also for large earthquakes, at least for the shallow sections. About experimental results. So what I will discuss mainly is what happens at a fault patch when the rupture propagates from the hypocenter at some speed of some kilometers per second and hits the patch. What happens? So this can be a some kilometer depth. And we can think that there is an initial stress that is loading the fault patch, but because of the rupture front propagating, of course, the shear stress increases until the rock yields. And at that point, the fault can slip. And this is a velocity function in red of some kind, like a Geophysique function. And the shear stress evolves, or maybe we can call it fault strength during seismic slip, and perhaps drops down, and then it tilts at the end while the velocity is dropping down. And so typical number for the slip on a fault patch is about, on average, is about 1 meter per second, but perhaps velocities can go for milliseconds up to 50, 60, who knows, meter per second. And because we are at some depth in the crust, and because of the slip rates, well, there is a lot of frictional power dissipation on these fault patches, so the order of megawatts per square meter, and this results in temperature increase and grain size reduction of the fault materials. And this helps a lot chemistry. Say both results in mechanochemical reactions, the contribution of thermal and mechanical energy. And this goes in emission of CO2 and other, in the case of carbonates and other processes. And to study these things, there are about 14 machines in the world dedicated to these studies. This is the one we built in Italy, and thanks to these European grants. And basically, it's in a horizontal configuration here. The machine weighs about 4 tons, it's 3.5 meters long, and the samples are the size of a glass of wine. They're about 50 millimeters in diameter. And white will be the calcitic marble, and gray the dolomitic marble. I will mainly talk during this talk. And the white one comes from a quarry that was made by Michelangelo. It's the same marble that Michelangelo used for the David, okay? So I'm destroying this piece of, that guy, of course, was a great genius. And so if you put the samples here, you can play with some velocities, because there is a rotary engine here that transmits the rotary motion to the samples. And you can play up to 6.5 meters per second, equivalent speed on this circumference here. And you can dissipate up to 300 kilowatts. And for the stress you can apply, that for this sample is about 40 to 60 megapascals, well, you can go up to hundreds of megawatts per square meter. So you can reproduce seismic slip conditions. And this is how the machine looks like today. So the samples were here. And this is the brushless engine is down here in the background. And well, you need about 300 kilowatts. So this is we have this dedicated inverter controller, and there is a separate line from the electricity that goes in the institute, because you have this kind of high powers dissipated in few, likely in very few hundreds of seconds or 1 second at most. And then there is also a vacuum chamber, so we can make some vacuum. By vacuum, I mean 10 minus 4, 10 minus 3 millibar, because perhaps we're interested in some processes, frictional processes, so you don't want air or room humidity. There is also a pressurizing circuit, so you can perform experiments in the presence of fluids. And also we have a mass spectrometer and so on. And Shiva, slow to high velocity machine, is here. This was printed by Stefan Nielsen when he was in Rome. And so this is a typical experiment when you put these two pieces of marbles. There is no confinement. I don't show any movie. I bored too many people in the years with these things. I just show some results when you slid the Michelangelo rock. And so this is shear stress, and this is slip. And the black line is the evolution during these experiments, because it evolves in this way, because there is some velocity function applied, in this case, this kind of strange function. So the slip rate goes from 0 to about 2 meters per second, and then it drops down. And you can see the strong velocity dependence of the friction coefficient. Friction goes down when the slip rate goes up, and then in the deceleration stage, slowly in this case, it goes up again until basically it's a strong healing of the experimental fault. And because of frictional heating, you can have breakdown of calcite, the main mineral of this marble, 99.9%, into lime and CO2. So there is gas emission. And in fact, Raihan in 2007, they measured these things, doing experiments with marbles. And you can see the friction coefficient dropping down and the emission of CO2. And the other important point is that the temperature, the bulk temperature, measured at some distance from actually from the slip surface, but it's a long story. However, at some point it increases, but it's basically constant at about 800 Celsius, which is the main breakdown temperature for calcite. So chemical reactions do happen here. And in fact, if you collect the sample after the experiment, this is calcite and this is dolomite, and now the scale bar is only 100 microns, and the slip surface was here and here for the dolomite. Well, you can see in these elemental maps the change in color. That means the concentration of calcium was pretty different, and especially in dolomite, it's very complicated. You have all these bands, sort of metamorphic reactions, actually. And this is because, especially for dolomite, you start to have even two reactions of breakdown. The first one, the dolomite breaks down at about 500 Celsius to produce periclase, magnesium calcite, emission of CO2, and at higher temperature, there is this magnesium-rich calcite that breaks down again to produce lime, like the same as this one, basically, but there is a bit of magnesium left. So there is a lot of chemistry also going on. Now, you can also do the experiments in a vessel, so in the presence of water in this case, and under drain and drain conditions. I won't talk much about this, but this is the evolution, again, in these experiments. Shear stress here, slip here, and there is a fluid. So for some experiments, we have also have the pore fluid pressure. Other experiments were run under vacuum. However, if you look at the evolution, there are some important changes here. I won't discuss these. But then, when the rock is sliding at some meters per second, in this case was 3 meters per second, it's not really important if there is water or not. The value is almost the same. And so this is something we would like to take in mind. You can also do experiments using other kind of sample holders using gouges. So this is a powder of the poor Carrara marble of Michelangelo here. And you can slit it again. And what you can see now is plotted the friction coefficient, which is simply, for me, is just the ratio of the shear stress or normal stress. So you can think of a shear stress here. The normal stress is kept constant in these experiments. And you can see the evolution. There is a peak value. There is some plastic deformation going on here. But then it drops down toward what we call, perhaps it's not a correct term, steady state, or it's pretty stable. And when the slip rate drops down, friction goes up again. So powders, fluids, doesn't really, in the presence of fluids, solid rock doesn't really change so much. So any process that you want to use to explain the response of marbles or these carbonate-bearing rocks during seismic slip, well, what we see is this, this pretty low friction coefficient, and also this strong velocity dependence. And also, we want this to occur in nature, okay? So we are not material scientists. Unfortunately, we were more rich if you do that. But this is what we try to do. So I will focus now on what happens here at the very beginning in Carrara marble. And we have this initial weakening, and the scale now is of the order of 100 micrometers, okay? 10⁻⁴ meters. And friction is related to the interaction of asperities at this scale. So something happens at this very small scale. And in the case of this initial weakening, probably processes like flash heating and weakening, they're relevant, flash heating. And these are short duration asperity scale process. And this result in very high local temperatures. And the temperature rises up very fast because the stress here is not a far field stress you can apply, maybe 10, 20, 40 megapascal, but it's a material property. It, perhaps for calcite could be of the order of 0.6 gigapascals, so very, very high values here. And then you multiply this by the slip rate and the contact time. Well, if you put some numbers here, you realize that you can easily achieve temperatures of order of 800 Celsius in basically milliseconds. And this was discussed quite a lot by Jim Rice, especially at the beginning, and comes from studies in metallurgy. So we can try to study these things by doing experiments where, again, you're familiar with this plot. This is shear stress and this is slip, where we stop the experiment at the very beginning. So there is a slip pulse here that is only 1.5 millimeter long, then another slip pulse with a different sample that is about 5 millimeters long, and then there is a longer experiment, and the velocity here now is up to about 0.8 meter per second, and lasts about 5 centimeters. Here the maximum slip rate was 0.2 meter per second, and you can collect a sample after each of these experiments and look at them, how the surface looks like. And in these experiments, we also use a mass spectrometer, and the sample was inside the chamber here. And these are the data from the mass spectrometer. And here I'm plotting now the slip rate, and this is time. So in this case, it's the same sample. There is a first pulse where the slip rate maximum was 20 centimeters per second, 1.5 millimeters of slip. Again, after 50 seconds, another pulse after another 50 seconds. And you can follow the gray curve, which is the CO2 concentration in the chamber, and there is already some increase. And when you do the longer experiment, which is only 5 centimeters, there is a huge burst of CO2, but also hydrogen and methane. This is pretty surprising because in the rock, in this particular Carrara marble, there is no amorphous carbon. And actually, we did experiments also without rock samples in the chamber. We don't detect any of those. So it looks like there is something related to the presence of water in the surface of the sliding surface, and this interacts with the contributes to produce hydrogen. It comes from breakdown of water, probably, at that scale. You can also look at the slip surface and dig with a focus ion beam scanning electron microscope. So you go at the nanoscale now, and so this was the slip surface, and you have these small samples. They are 15 microns, and you can look at them with a transmission electron microscope. The slip surface is up here, and if you zoom, now the scale is 500 nanometers. If you zoom, you find these nanoparticles. You can recognize the lattice and perhaps very few dislocations inside. And you can see this an experiment stopped here at the very beginning. And already you can see these kind of fractures inside the crystal. These are cleavage surface, bent, by the way. And there is a sort of a concentration of dislocations here. And the original grain is bigger than this room. Okay? It's about 200, 300 microns, so much, much bigger than this. So this happens already at the initiation of sliding. And okay, these are other details, and I can go directly on this one. And when you stop the experiment at 5 millimeter, you find also amorphous carbon. And some of this amorphous carbon is some strange feature here. It's a sort of post-deformation feature. However, perhaps there is also already something produced during sleep. So this is shear stress and this is sleep. And we're looking at something that happens in the very first millimeter of sleep. And already a lot of stuff is occurring, nanograin formation and amorphous carbon. And however, the bulk temperature, if you measure it, which is pretty difficult, but if you model it, which is easier, should be less than 20 Celsius in the entire sleeping zone. However, at the asperity scale can be much higher. Now, what we think is going on is a sort of fast-moving dislocation model where there is the birth of dislocation because at the asperity contacts there is an abrupt increase in strain rate, and they start to pile up along a cleavage surface or grain boundaries. And at some point, the concentration is and the stress exerted by the dislocation is so high to overcome the yield strength of the cleavage surface, and so you can trigger what people call dislocation avalanche from metallurgy. Well, basically, dislocations are migrating very fast in the lattice, and this release the kinetic energy is converted in an increase in temperature inside the lattice. All this can happen in milliseconds and less, according to modeling did by metallurgists. So this could explain very local high temperatures and the formation of these nanoparticles. So it explains also this burst of CO2. That would be pretty difficult to explain, at least for me. What is also interesting is that amorphous carbon is also lubricant, and perhaps it's just in the right place to help initial weakening of the fault. So it's very difficult to estimate the temperature associated to the dislocation avalanches, because you need to know the density of these locations, you need to know their velocity especially, which is very difficult. They can go up to sonic waves. So you can play quite a lot with these things. However, if this is the slip surface, now I lost it. Okay, so this is the bulk temperature. At these asperities, because of this process, maybe you can be much higher at that scale because of fast-moving dislocations. Then we can move towards, from this initial part, when you already have a lot of nanoparticles ready, and the temperature is increasing, the bulk temperature, for perhaps grain size dependent process. And so I will focus mainly on what happens, what we call in these terms, we use this term steady state. So this is the calcitic marble curve, and dolomitic as a slightly different curve at the initiation, but then they just overlap, given the same velocity function you apply. And this is their evolution of shear stress versus time. And what is interesting, if you do many experiments, when you apply 10 megapascal normal stress, 20 megapascal, 30 megapascal, and so on, it looks like the dependence of the shear stress with normal stress is negligible, and especially when the slip rate is high, is absent. It looks like it's independent of the normal stress. And this is typical of crystal plastic processes. Just this kind of diagram suggests this. And when you look at the samples after the experiment, and you can see this, what I call the slip surface here, or the mirror-like surface, or the surface here, and just beneath, they are pretty similar. This is calcitic marble, and here we have dolomitic marble. There are some small differences. These two rocks were formed under the same conditions of displacement, normal stress, acceleration, and so on. And you can also collect, collect sample at the surface and dig with the field, the focus ion beam, and do some transmission Kikuchi diffraction, electron by scatter technique. This is one of the first times applied in geological materials, is to basically to measure the orientation of the grains. And the scale value you can see is about 2 microns, and so some grains are about 100 nanometers or less. And you can appreciate that the same color means that, similar color means that they have a small misorientation angle. So the lattice is slightly misoriented in these grains. And you can plot this data using many other data sets, actually. And unfortunately, there is a problem with the conversion of the PDF files. But there is very weak lattice preferred orientation. And this is consistent with some kind of diffusion creep process. Moreover, you can see the straight grain boundaries, few pores, triple quadruple junctions. These are typical of superplasticity behavior, or basically grain boundary sliding and diffusion creep. So it's a crystal plastic process that is occurring. And people already discussed these things, and like Harry Green and Nicola De Paula. And well, you can try to use a sort of flow law and to describe what is the shear stress you would expect at a slip rate, in this case a strain rate of some kind that you achieve in these experiments, given a grain size. And as you can see, bigger is the grain size, bigger will be the flow stress, and also with temperature. Higher the temperature, lower will be the flow stress. And so you have these kind of terms, and you can use equations, and this is the same flow law for calcitic marble and dolomitic marble using data from the literature, where this is the activation energy of diffusion processes. And actually, it's a strong extrapolation because data from the literature come from experiments that were run at very, very low sleep rates. So it's a very strong extrapolation. But what is interesting is the values you get of about 1 megapascal, similar for dolomitic marble, and this is what we measure. So it's curious, and there is a lot of work probably we should do here to understand more what's going on. At the very end of sleep, we observe healing, and this is when, of course, the sleep rate decreases. And also temperature is evolving, according to some models that Stefan Nielsen did years ago. And of course, because of this kind of very strong exponential dependence of temperature, you would expect this to happen. A small difference in temperatures result in abrupt increase. So you can explain also the healing at the end of sleep. Moreover, at the end of sleep, in the sleep surface, you find this kind of beautiful features. The scale bar now is 1 micron. And perhaps they are also related to sintering, I think also at the end of sleep. So the crystal can grow and it's under almost static conditions here. And now this is the sleep surface, and you can appreciate how many pores are there. And so the elements can easily diffuse inside pores, probably, rather than diffusing along grain boundaries, which is slower, of course, and especially inside the lattice, which is very slow. So this is an efficient, mass transfer process. Perhaps is propelled by the CO2 gas exhaust that you have during the carbonation. And this rapid results also in rapid sintering. You can make some calculation, actually, is what you expect in terms of growth of grains, is to observe in these experiments, this kind of fabric here. So the question is now, do they happen in nature? Well, these are some experiments we did in the past. This is a natural mirror surface, and this is what you see when you make a thin section and look at the rock. This is the mirror here. So it's perpendicular to the sleep surface. And you can see truncated grains like this in natural rocks. And actually, this is something you can reproduce somehow in the experiments. There are some more cracks here. Of course, there is no healing for these cracks, while here you have, a millennia to do this, perhaps. And then you can also look at natural examples of sheared calcite veins like this one, and they're just very similar to what we find in the experiments, also at the same scale. There are a bit more pores here. Or if there are mixtures of calcite here in white and in black is the dolomite, you can see similar flow structures produced during simulated earthquakes in the lab. So maybe there is something we are actually reproducing in our experiments that happens in nature during earthquakes. So to conclude, destructive earthquakes, they occur in faults cut in carbonate. So clearly there is an abrupt acceleration, and this probably results in temperature, in high temperatures sometimes, but especially in the possibility of triggering some temperature-dependent processes. And in particular, the fact you can develop also, there is perhaps amorphous carbon, but especially nanoparticles, they can really be extremely active in grain size dependent process and temperature dependent process. And this is probably the main thing. And what clearly the message is there is a lot of crystal plasticity going on during earthquakes, where geology think earthquakes are brittle, perhaps. When you look at that scale, they aren't anymore. So they're ductile. So thank you very much for your attention.